So I said on the last video, notice we've already defined this difference. UFG, well, UG minus UF has already been computed for you in most tables. If the UFG value is in the tables, just use it. You can compute the difference between these two and you will get to the same conclusion mathematically. If you take this value minus that value, you will get this one. But it's already done for you, so if you want to use it, feel free. We could do it for H if the problem needs me to find H values. When we get later in the semester with Chapter 7, we're dealing with entropy. I can also do this with entropy values. Again, UHF and S, UHV and S all behave about the same way as we see down here on this diagram. Right? U, V, H, and S all behave about the same way. If I can find one, I can find the other three. If I'm in this dome region, here's how I will find it. Okay? Notice what happens if I will not have a quality value outside of this range. It will always be from 0 to 1. Quality makes 0 sense for a superheated vapor. Quality makes no sense for a compressed liquid. It's only for saturated situations. Now, if it's a saturated liquid, notice what happens if I plug in UF here or VF here. VF minus VF is equal to 0. That's here. That's the lower limit. A saturated liquid is the lower limit. That's where you have a 0. A saturated vapor, if I plug in VG here, VG minus VF divided by VG minus VF gives me 1. An X of 1 is for saturated vapors. Quality is the portion in the vapor phase, meaning that if I have a saturated vapor, 100% is in the vapor phase, I should have an X value of 1, or 100%. This represents the percent, if you will, in the vapor phase. So if I get an X value of 0.4, that means 40% is in the vapor phase, 60% is in the liquid phase. So again, it only makes sense if I'm dealing with something that's at the saturated point, at the boiling point. I don't use it for superheated vapor or compressed liquid. Okay. So here's another problem. Water at 170 degrees Fahrenheit has a specific volume of 50 cubic feet per pound mass. Determine the pressure and internal energy of the system. Okay. Well, more property tables up here. I've got water in English units. Okay. Alright, so I'm going to set this to the side. Okay. Another example here. L5 and 6. This is page 6. Given. Problem had given me temperature, 170 degrees Fahrenheit. Specific volume. I know it's a specific volume because this is it's in units of volume per mass. It's 50 cubic feet per pound mass. A specific volume of 50 cubic feet per pound mass. Okay. Now my substance is water. That's given also. They want us to find, so the thing they were asking for is the pressure and the internal energy. Okay. Well, what do we know? We know our substance. I know two properties, specific volume and temperature. So I need to figure out which row, which table. What is the state of the system? So which row, which table? To do that, I need to know the phase. I know I've got English units. Okay. So to determine the phase, I have a temperature and a specific volume. So I need to know where am I at relative to the G and F values. Well, let's set this up here. Is that on the screen and glaring? No, good. Okay. So, I've got 100 and, I know you guys can't see this very well, but I'm going to set it here so I can see it right now. Okay. I've got 100 and 70 degrees. That's over here for me. Okay. So I'm going to put these on my diagram. So my temperature we said is 170 degrees. If you go look that up in the table, the saturated vapor specific volume is like 61.982. And the specific volume for saturated liquid is 0.01645, so 0.01645. What do I know? Well, I'm in here at 50. These are all cubic feet per pound mass. So I'm in here at 50. What does that tell me? I've got a mixture, right? So the phase is a mixture. So I don't know how much is in the vapor phase and how much is in the liquid phase, but we can figure that out. I can say, well, I know my V value, so V minus VF divided by VG minus VF, that gives me the quality. And what I really want to know here is the U value. So given the quality, then I can use that to find the U value. Using U minus UF over UFG. And I can go look all these up. Okay? So, V minus 0.01645 divided by 61.982 minus 0.01645. Right? And I guess you could write in here V. It's easy. I'm just going to scribble over that. That's 50. I'm going to write my units one time. So I'm just going to factor them out. Those are both cubic feet per pound mass and cubic feet per pound mass. Since I'm writing it twice. That's equal to X. So I can find my quality directly there. I've got a calculator. Here it is. Well, let's just use my phone. The app shows up better than my regular screen calculators do there. So make sure I don't have a glare on that. Okay, I do not. So my quality there. So I'm going to do the bottom first. That's 61.982 minus 0.01645. Okay, that's the bottom difference. I'm going to reciprocal that so I can multiply that to the top. And the difference to the top is 50 minus 0.01645. And multiply that. So I get a quality there of, you can see, 0.8066. That's my quality. So I'm about 81% in the vapor phase. Now, I can then use that quality to find my unknown U. So if I solve this expression here, U is equal to X times UFG plus U sub F. You want to do the algebra ahead. I know my X is 0.8066. Multiply that by my UFG value. I'm going to go look that up. I'm getting 927.08. I'm trying to do this quickly so it's possible I'm getting that wrong. I'm looking at the wrong row, but I think I'm getting 927.08. That is BTUs per pound mass. And add to that then the UF value, that is 138 even BTUs per pound mass. Okay. So I'm going to take this, multiply it by this UFG value, that's 927.08. Add to that the 138 for U sub F. And I'm getting about 886, give or take. We'll say 8. U is equal to 885.81. That's too many significant digits, but that's okay. For this case, I wouldn't go, you really shouldn't go more than 3. 5 is probably excessive, right? 885.8 or 886 would both be okay. Okay, what else did we want? So that's one answer. What else do we want? Find pressure. The pressure, in this case, because it's a saturated mixture, if it's saturated anything, the pressure is going to equal the saturated pressure. At 170, it's basically 6. It's 5.9999. Yeah, 5.9999 psia. And those are my answers. If it's a property if it's values out of the property table, all of these digits are significant. If it's a final answer like this, I would say no more than 3 significant figures are useful. If you want to write, I would probably count you wrong if you gave me more than 5, right? If you gave me past this 4 here, that's wrong. But, 3 to 5 I probably wouldn't count wrong, but I might caution you against using 3 unless you've got a good reason. How are we on time? 3:30. Okay, we could start the next one. Okay, so, all right. The next scenario, so again, that's one scenario where you don't fall exactly on a value out of the table. So what's the next scenario? Well, the next scenario that if you don't fall exactly on a value that's in the table would be where you would have to interpolate. So let's say I've got R134 at 50 kilopascals and 37 degrees C. Okay, well, I'm not going to write out everything here. You can draw the diagram if you like. Right, so again, I'm hoping at this point you've got your property tables out, you're following along. And how do we do this? Well, we need to know. Something like this. You've got R134. I've got a pressure and a temperature. I need to know which table, which row. So I need to figure out the phase. Well, I'm given a pressure and a temperature, so I'm going to look at one of these kind of diagrams. Okay. Well, R134A, metric units. R134A, metric units, 500 kilopascals. R134 boils. The saturated temperature for R134 at 500 kilopascals is about 15.71 degrees C. We're at 37. So that puts us in the superheated vapor region. Right? R134 at that pressure is going to boil at 16 degrees C, and we're up at 37. So what that means then is we're going to go to the superheated tables. So if you look here in the superheated tables, and I don't know how well you can see this, but you've got R134 superheated tables, 0.5 megapascals, that's 500 kilopascals, and I've got a temperature of 37. I've got a row for 30, and I've got a row for 40. Imagine how long this table would be if I had a row for every single degree or every single tenth of a degree. It would be huge. There's no need for that much information. They give you a row for 30 and a row for 40, and you can approximate in between. Now the common answer is, Steve, why don't we just average the two? Well, that would be wrong. You can do better than that. What are we looking for? Well, all right, let's write these things down. Okay. So what are we looking for? Well, again, at 500 kilopascals and 37 degrees C. We know we've got superheated vapor. Again, this is R134A. Okay, I've got superheated vapor. Now I've got a row for 37. So let's say I plot over here, and let's say I plot T and V. So here's what I know. I've got a row for 30, and I've got a row for 40. And I've got a data point, V at 30, and I've got a data point, V at 40. So I've got these data points. We're going to pick up there on the next video.